Right, so the next talk we got from Nawal Husnoo from the Met Office on detection of wind turbine contamination using spectral dual polarization and a convolutional neural network. Thanks.
Yeah. So I thought I'd add some introduction after seeing all the good talks yesterday. We produce at the Met Office a surface rainfall rate every 5 minutes. A composite across the entire UK, and there are 18 radars that contribute to this. We have quite a large variety of customers who make use of our data, and we also provide Doppler wind measurements, so that's just measuring the radial velocity of the wind from each radar, and that goes directly into numerical weather prediction. So we're actually fortunate at the Met Office in that, unlike most Met services around the world, we actually design and build everything in our radar. So we control the entire instrument, so we can make it as good as we want it to be, as good as we can afford to make it to, I guess. We write every line of code in the firmware. We write every line of code that runs on the site. So this receiver sits on the back of the radar dish, which rotates about once every 40 seconds. And we have some signal processing going on. There's a desktop computer server that does the signal processing. So at this stage, we produce about 300 megabytes of data every 30 seconds. And we can't bring all of that back to Exeter. So what we do is that we produce a bunch of products. We call them the raw products. And they generally measure a bunch of things like the amount of power in different channels. And then we bring all of that to Exeter, so we bring about 1 megabyte per site every 30 seconds or 40 seconds. And then we do some quality control based on the data that we brought back. And then there's a whole bunch of other clever things that have to go on, because we want the rainfall rate at the surface, not up in the atmosphere where it was measured by the radar. And then when all that's done, we then stitch them all together into a composite using the best data that's available for each location. So in this talk, I'm mostly going to be working around this area here. About 15 years ago, we upgraded the entire network to dual polarization, which gives us a horizontal and a vertically polarized signal that allows us to do a bunch of cool things. I won't go into the detail of what these things mean, but they are parameters that there's 3 at the bottom. They are parameters that you can derive from using this dual polarization upgrade, which we've had working on all sites for about the last 10 years or so. And the reflectivity, which is the original product from radars. You can see over here, if you know where to look, this is actually stationary ground clutter, this is rainfall, and this is rainfall. And if you look at the new fields, these new parameters, you can see that there are different signatures between those 2 areas. So that's what we can use, and that's really improved our quality control, so that what goes into the composite is really just rainfall. Except it doesn't actually work for wind turbines, and this is where this particular talk comes in. And we've been working with Sebastian and David in the US in the National Severe Storms Lab. Couldn't have done this without them. So wind turbines are a problem for us with the radar community across the US and across Europe more recently. So obviously with our net zero commitments, we expect to have bigger and taller wind turbines, bigger wind farms, more of them. And they're creeping really close to our radars, which makes us nervous. But of course, they are an important thing. We can't really get rid of them, so we have to learn to live with them. And they are very difficult to detect and censor or remove in the data based on the conventional dual polarization and other techniques that I've already talked about. So yeah, we're relying on a fixed mask that we have to update every time somebody says, oh, there's a bit of something there. Is that a wind turbine? Oh, yes, it's a wind turbine. Put a mask there to make sure that's not getting through the data. And there are a bunch of problems with that, because it assumes, for example, that the atmosphere is always in a static state, but in practice, the beam from the radar can move up and down based on the temperature profile and the humidity profile. So we don't really want to be always throwing away the data when there are days when actually we need that data when there's rain on that area. We kind of want to keep it. So the reason we want the lowest elevation data is something like this. Close to the radar, if something isn't your way, you can look further up and you can see, okay, this is still representative of what's going on the surface, because that's where we care about. Further away from the radar, unfortunately, in this extreme case, you can see that we've completely missed the weather, so it would really be good if we could sometimes use the lower elevation data when it's good enough. There's a technique called Doppler filtering. So instead of looking at the absolute power, we're now splitting this into a spectrum. So we're doing it's a Doppler spectrum. It tells you, in this case, the weather is over here. It's moving at some positive velocity away from the radar. But the stationary ground clutter would add some power at zero velocity over here. So the idea is that you know where it is. It's going to be near zero, so you can notch that out. Just remove the data, and then you can interpolate across that, and you can reconstruct your spectrum. And that kind of works for rain and stationary ground clutter because of the zero velocity. But you don't always want to turn it on, because sometimes you have this thing called the zero isotope, where the rain is moving perpendicular to your radar, and because we only measure radial velocity, then you might accidentally remove that data when you don't want to. Much worse with wind turbines, you've got this multimodal kind of mess. In fact, the data looks a bit like this, and this is S-band, which is what the Americans use, and you can already see the mess there. But then C-band, which is what we use, it's even worse because it just aliases over and over. You don't need to know the details here, but basically it's a hard problem to do with conventional approaches, which is why we are throwing machine learning at it. And in this case, we need the solution to run in real time. So I've got like 0.1 of a second to classify every single pixel along a radial, and that's not a lot to work with. And therefore I have to work with a smaller model, which actually I think is a benefit here, because a lot of people just reach for the big super duper models, and I think that's not a good idea, because firstly you're wasting a lot of energy and a lot of time on it. But if you can use a more understandable, a smaller model, you should always use that. So to train this model, what we do is we measure rainfall tiles, cutouts of rainfall where we know there is no ground clutter or wind turbines. And then on a dry day, we take data where we know there is ground clutter or we know there is wind turbines. And we combine those two tiles and we get these contaminated tiles. And we've already published that in a previous work, doing a slightly simpler problem. So the idea is that you have the original rainfall tile, so that tells you how much rain you should have after you've chosen the right one at the end, if you've filtered it correctly. I won't go into the details here, so this is the same job polarization stuff I talked about earlier, the spectral version of that, which is what we're using as input to our neural network. So you might notice that this is actually a really, really simple model, just pure convolution blocks, and all of these frequency components that I talked about, and we also have the original powers that we measured. And the aim of it is to really tell us just one of these four outputs. So if you're looking at it as some new data, we're asking the network, tell us, is this just pure rainfall? Can we use it? In which case we're going to call it unfiltered. We're just going to use that data as it is. But remember that filter I mentioned earlier. Sometimes it works really well. So in which case the filtered version is better, because the original version is contaminated, the filtered version is good, so we'll use the filtered version. But it doesn't always work, and like I said, it doesn't really work at all for wind turbines. So in this case, you might want to just not use that data and go to the higher elevation and take the risk that it might not be as representative as we want. This is a dry case, and we happen to know there are giant wind turbine farms here near the Isle of Man. And the model has flagged it as in black here, so that will be where the wind turbines are. There's a couple of false positives, but there's a couple of land turbines as well. And most of this is just going to be ground clutter over here, and these are the wind turbines. And then when there's rain on top of it, you can see that it still flags some of them as wind turbines, but in some cases it says actually the filtered data is a bit better, so we can use that. And over here, all of this ground clutter stuff is using the filtered data. Down here it says that's still ground clutter, because here there's no precipitation on it, so let's just give up on that. And so this is a fixed mask at this radar is called Turnham, so this is out in the North Sea. And there's these giant wind farms, some of them quite far away. So these ones actually don't show up very much at all. It's only, I don't know, a couple of weeks a year where they actually show up. And because they're there, we have to make the mask cover them, because otherwise they would show up. And you can see that this is the new version has detected a whole bunch there. But these ones are actually very faint, so it only rarely picks them out when they turn up, basically. I mentioned before that if we give up, we might miss the data entirely if we keep going higher and higher in elevation. So you can see these big gaps in here. That's where the existing mask has completely sort of worked against us. It's deleted all the data. Whereas with the new scheme, we've filled in some of these areas there. And you can see some of these, I think these are ships, like these are shipping lanes. They've been quite attenuated in this case, so this is a good thing. Unfortunately, this one there is now brighter, and there's that ring around this one here which has shown up. So that's a problem of machine learning, when it really does learn exactly what you teach it. And in this case, I've managed to track this down to a choice I made when I was deciding when to use the unfiltered data, when to use the filtered data. I actually was quite lenient with the filtered data. I said, oh, let's put the threshold up here, which is fine, just use the data, even if there's a little bit of muck in it. And it turned out that's come back to bite me. And I've gone back and retrained it with a lower threshold, so I'm a lot more strict now. And unfortunately, I don't have the pictures to show you for this one because we're still in the process of deployment again. But this has worked really well. And my message to you really is reach for the simpler models first, and then you can always get a better one and see how far you've gone. And yeah, good luck with that.
Great, thanks for that. Okay, so we've got time for a question or two. All right.
Yeah, just curious about your convolutional neural network, what the architecture is like, one that's already well known or one that you just created.
I did just build it. It's like basically whatever they were dealing with in 2012, roughly. It's really simple. So it's got a whole bunch of inputs, and it's got these 4 channels. So imagine this being red, blue, green, and extra. And this is just a cutout of an image. And, 5 times 3 is 105 here. In range of and the convolution blocks are just 3 by 3s with some batch normalization, reduce.
Yep.
So in this case, because we have these 2 different, I feel almost like I can almost call this multimodal here, based on yesterday's talk, because what we're doing is I'm using global max pooling to drop down all the parameters into just the feature vector. So it doesn't care how big, how many points you had on the original, it just has whatever 8 features there, and then it's got 8 features from this one. You can concatenate them, and you have a classifier, which is the dense one there. So it's really the dumbest possible convolutional network you can make, and it works incredibly well.
Other questions? You can shout at me if I fail to spot your hand. Well, I've got a question, but it's a kind of a low-tech question. I was wondering, would it be possible to actually mount the radar on top of the wind turbine anyway? And then does it just need to have like line of sight over the blades?
Yes and no. Yeah, so you want to mount them higher than them, is that what you're saying?
Yeah. Well,
I mean, they already are on quite a tall tower, and it gets complicated because those turbines are like 100 meters across the blades, and about 100 meters up or whatever. Yeah, so it's quite difficult to do that. Yeah.
Yeah, fair enough.
Yeah, generally we have some rules around how close to the radar they can put them, but they're always pushing the limits and always trying to say, oh, but about this one, this other radar nearby.
Yeah, no, I see.
But
Well,
the problem is that it keeps growing, and so we kind of need to learn code.
I was wondering if, like, the turbine tower itself is already 100 meters up. Maybe you could just stick something on a pole at the top.
Yeah. Oh, right. But the radar is actually quite heavy, so I don't think it would. I don't think you could put it on all those.
Yeah. Right. This is why no one asked me. That's fine. Okay. Oh, yeah.
At what stage do you deploy this? Is this done in that because I know you mentioned that you only get sent back to Exeter a certain portion of the data. Is this deployed on site or in Exeter?
Yeah, so this one is running on site, and we don't even have a GPU on it, which I'm still sort of trying to get people to fund it. But basically, first I would need to show some result that says I need a GPU, but it turns out so far I didn't. This works quite well. So yeah, this is running outside. This is using the 300 megabytes of data I mentioned, basically, because that's where the spectral information is. Because when you get to the raw products here, there's basically nothing left for that sort of approach to work.
Yeah. Presumably, it saves you having to send a lot more data back.
Right. So what we're doing is we're trying to maximize the information that we can extract from that big bulk of data and send back one field that's got 0, 1, 2, 3, and it says 0 is use the data, 1, use the filtered version, and so on.
Great. Thank you.
Let's thank Nawal again.
Thank you.